Okay, I think we're ready to get started. So thank you for joining us today for this session on large facility decommissioning. And we're going to have a short video now, thanks to our sponsors, S2 Environmental. Wonderful, thank you. So we should have Paul's presentation rolling here right away. Okay, so for those of you that are joining us in this session, we're shifting gears here a little bit to have a dedicated session to large facility decommissioning and closure. We will have in this session 3 speakers, and then we'll have to do something a little bit different. We'll be having a panel with 3 of the speakers, as well as 1 additional with a slightly different area of expertise to round out the panel discussion. Would recommend or hope that questions can be asked at any time in the GoToMeeting question section. So this session originally came about to focus on sulfur impacts. It was to follow the emerging contaminants presentation that Matrix Solutions and I did in late September. And then as we started putting together presenters in the session, thinking about whether there were 4 sessions worth of sulfur content, it became apparent that we could really broaden out and we could talk about some different things and put a bit of a different twist on, I guess, the scale or scope of presentations that we could give. And so really happy with how it came to be. The 3 presenters will, the 3 presentations really kind of play off of one another, I think you'll see, and really go to inform the panel at the end. So hoping that folks will be able to stay with us for the whole session. So why large facilities? And by that we mean gas plants and processing facilities. We see this as an issue facing industry and service providers. They are unique. So for those that have worked on these large facilities, know that they really do present some unique challenges in terms of having some different or unique contaminants and byproducts of those contaminants. Obviously, you have a lot of infrastructure. Sometimes that has been removed for the most part on the surface, but oftentimes underground, there still remains a lot to work around. Large volumes and areas. So a typical well site is one thing, but some of these are multiple well sites in size, and so decisions that are made in terms of remediation and assessment and and management of these sites, it has a huge implication if you go one way or another, just due to the volumes that you can be dealing with. Some of them, particularly the older facilities, have some long-standing plumes to be dealt with, lots of data, so multi-year data, complex data sets, and again, sort of multiple sites within a site that present some unique challenges. We also have regulatory reporting that is quite rigorous for these sites, so there's a lot of information that's been gathered over the years. We have significant amount of discussion that needs to happen with regulators in terms of how the sites are managed. And often we have multiple stakeholders. Next slide, please. And one more click. So in terms of liability, I guess that's really where some of this discussion was driven from, was looking at on a provincial basis the liability that we see, that we hear about in the news related to oil and gas, and how much of that is attributed to these large facilities. We hear about the well sites, but there is quite a substantial portion of provincial liability tied up in these large facilities. We also know that they're aging, many at the end of their productive lives. And I guess the goal of this session is really to look at some of the innovation opportunities in this space and how we can more strategically manage these sites. So exposure control and sites that remain in sort of perpetual management. We have to ask ourselves, is this what we want on our landscape, or do we want to see the end of these sites to closure? And that's truly, I think, where a lot of them need to go. There are obviously some impediments. Some of them, there's a little bit more incentive in terms of brownfield and land value. Some of them are more remote and require potentially different types of management. When we think about the efforts that we're putting into well sites and associated facilities, we're looking at process efficiency, technologies and digital data, management, collaboration opportunities, and really leveraging collaboration in terms of the way that we're working, the way that we're innovating, and then also bringing sustainability into the mix as we start talking about environmental and social corporate governance.
You have one room to check.
So, sorry, we have somebody with their mic on there. So when we think about the innovation opportunity, we're thinking about on-site technology. What can we bring in to help facilitate this work in terms of sampling, testing, and data collection, data management, analysis, modeling, and communication tools, and essentially having more tools in stakeholders' toolboxes for managing these types of sites. And really, if there are tools that need to be developed that are publicly available, what do those look like? How do they get developed, and who would be using them is one of the questions that we're asking here. How can we make these tools more available to those that need to use them? I'm just going to put in a quick plug here for the Clean Resource Innovation Network. There's a novel land and well site reclamation theme that is really aimed at integrating technology for management of well site and land reclamation, and would hope that those of you that are interested will sign up online to be informed about CRIN and the things that they're doing for managing our hydrocarbon resources, clean hydrocarbon resource from source to end use. And I will pass it on to Paul to continue with this presentation. Thank you.
Wrong time.
Thanks, Simone. Hopefully you can all hear me, and hopefully we get some of that background noise taken care of there with. Yeah. So again, I want to thank.
What's a live event? People are going to look back and go,
yeah. I want to thank Simone and Initech for having me here, first of all, and I want to thank RemTech, as always, for the forum to share our knowledge and the opportunity to learn from our colleagues and peers. So I'm going to be speaking generally about the reasons that decommissioning these large facilities is difficult, some of the barriers that we typically run into, and some of the reasons that liability estimates can be inaccurate. I'm going to cover the common issues that we see and potential ways to overcome them. But before we start, I want to pre-answer some questions that we often get asked. Yes, these are real tools and the data is from real sites, with the exception of the next slide, which is kind of an analog just to frame the issue. Yes, we have closed real sites using these techniques. And finally, yes, we would be happy to provide references from both clients and regulators prior to starting work. So I want to answer those questions for a few reasons. One, we get asked them all the time. And two, they're valid questions. You should be asking your contractors these questions, particularly before you embark on trying to close something as complicated as a large facility. So moving in, so this is that analog that I was telling you about. This is just this is a gas plant site that I grabbed so that we could have a look. Large facilities are complicated, as Simone said, and typically what happens is everything that's kind of above a generic guideline, it gets called a source and added to your client's laundry list of responsibilities to deal with at the end of life. There's a lot of potential parties, responsible parties on a site like this. So if you look at number one here on this slide, that's the heart of this issue. That is a gas plant. That's going to be your client's responsibility. That stuff that goes on in that large rectangle is likely the responsibility of your client. Number two is you see a telecommunications tower there, and sometimes those are custom built for the plant, but just as often I've seen them owned by a third-party telecommunications company. So someone puts up a cell tower or something like that, or even a radio communication tower, anything that happens on that site would then not be the responsibility of your client because it's from a third party. Number three, there's a number of skids in there that look familiar to me, but regardless of that, you need power. You need a lot of power on a site like this. And typically that power is provided by a power company. And so they'll have a number of skids on site using fuel gas or usually with backup diesel to provide power to the site. So you're either going to have a substation if there happens to be poles and wires in the area, or you're going to have skids like this. But either way, not your client's responsibility. Whatever goes on that little piece of land, whatever releases happen, are the responsibility of that power company. Number four, it looks like we've got a campsite here. Again, something this large, there's a good chance that it could be run by a third party. If it's run by a third party, then it's also the responsibility of that third party.
Its members' ability to hold safe functions and events in the province. In a release, the group says at least 11,000 events worth $193 million.
I think we've got someone from another presentation in
authored a relaunch strategy aimed at
so number four there, again, that's campsite. Number five, that is completely fenced off. So I would say that is, again, that's a third party site. Anything that goes on there comes off that site onto your site, not your client's responsibility. Number six is a tank farm. Now this could be a run at the plant, or it could be a midstream company. So just rattling through those quickly, we could have 6 or more responsible parties on this site with potentially and even likely overlapping and commingling plumes. So I talk about myth, legend, and recurring revenue. So the myth and the legend is often when people are working on this site, they'll go talk to operators and maybe some, they'll have a hit for some weird parameter and they'll go talk to an operator, and an operator will say, oh yes, maybe it's possible so-and-so threw something in the pond to kill the algae at some point or something like that. And so then this sort of mythology builds up around this site. So you find chemicals that are elevated, and then you start inventing sources to account for them instead of doing it the other way around and trying to work back to actual sources. And so you've got all this myth and legend that then has to be explained. And then there's many chemicals that are used on a site like this. And again, they could be attributable to various parties, and those chemicals then oxidize or otherwise break down into other chemicals, and everything has to be traced back to its source. So the chemical that you're measuring in a well has to be traced back to the source chemical that it originally came from, and then that source chemical has to be attributed to a responsible party. So so there's multiple specialties are required typically to do this. You know, you need to stay in your lane. You need to do what you're an expert at, and then fill your team out with other experts to help. And and this is not an easy thing to do. Large companies don't like to sub out stuff. We want it's not human nature to want to keep as much revenue in house. But on a site this large, you're going to need a lot of bench depth. So you're going to need a lot of experts to work together as a team. So where does that leave us? Just sour gas plants. We have around 350 sour gas plants in this province. And so far, can you guess how many of them have achieved full REC certification? Yeah, the answer is 0. So, and this doesn't even account for all the large storage facilities, brine ponds, and other facilities that require registrations, like like sweet gas plants and things like that. So that's a problem. So how do we solve this problem? There's 3 questions I think that we need to answer. We need to make it simple. So we need to break it down to 3 questions we need to answer on a site. It is a problem of resourcing on the regulatory side for sure. I mean, but this is not a new problem, because regulatory agencies have never been and will never be resourced to do the work for us, to determine risk for us. And I think the main problem as consultants is we often don't answer the 3 questions on this slide clearly, concisely, and credibly. Is it background? Is it someone else's responsibility? Once you've answered those 2 questions, you know what your client's responsibility is. Once you know what your client's responsibility is, you can look at those elevated chemicals and say, do they even pose a risk? But you need to do it stepwise. And so then this goes back to multiple specialties being required. We just need to stay in our lanes. So now we're going to go through some sites with some real data and answer these questions. Is it background? I'm not going to spend too much time here because I've given a number of presentations on this, as has my my business partner, Court Sandow. So this is a process. This is some multivariate statistical analysis, but when you put it together in the way that it's done here, it's a proprietary process developed by our partner company, Court Sandow, at Chemistry Matters, developed this process and licensed it solely to our company StatViz to commercialize. And there's a reason why it hasn't been released broadly, and that's because it's easy to go wrong with this process. So you might look at this on the left here at the hierarchical clusters and think, yeah, I can see longer lines are less similar and the shorter lines are more similar, and I can see the major groups of clusters there. I can see the groups of clusters there, so I know what those groups are. And likewise on the right, you can say, well, I could draw a line around those clouds. We've got sodium and calcium chloride pulling down and to the right, our vector plot there. And then we've got sulfate down and to the left, sorry, and then we've got sulfate pulling up and to the right. So we're just going to draw a line around the cloud of sulfate-based samples and call those background, and around the chloride-based samples and call those impacted. But what you don't see, is in the background the 4 different ways we normalized this data set before we arrived at an answer, and then the 2 or 3 hours that were spent between Court and myself and our data analyst trying to poke holes in every theory that was put forward until we found an answer that we knew we could credibly and defensively put forward to the regulator. So from here we get our groups of what we think is background, and then these are again, this is a proprietary tool developed by Court at Chemistry Matters, and their radar plots for salinity fingerprints. Sodium and chloride pull up and to the right, and sulfate pulls down and to the left. Now on a well site like this site is that we're looking at, any sulfate salts would be considered natural. And you'd use those to come up with maybe some background guidelines for EC and SAR and be on your way. But of course on these large facilities, if you need to know about that oxidation process and if If you happen to handle elemental sulfur on your site, well then you know that elemental sulfur is gonna break down into sulfate. Eventually, it's going to oxidize down into sulfate, and so that's why I say trust the pattern within reason, because these patterns tell us a lot. But if you just said that everything with sulfate was naturally occurring, you could end up coming forward to the regulator with a sulfate guideline on a site with a sulfur pad, like we're talking a lot about in this stream, in the tens of thousands parts per million, and they're going to look on that skeptically, and rightfully so. And so, that's going to cause them to call all your other science into question, and then you're going to have to, it's going to set your program back, and you're going to need to start over. So that's one way to look at background, and trying to figure out background on these large facilities, just like the answer to every question here is more difficult than on a small site, on like a standard well site. So moving on to the next question, is it someone else's responsibility? We're going to look at some hydrocarbon sites now. So this is a large facility that handled crude only. They only handled crude oil. And if you look at on the left there, so if you're doing spill response, this is a lot easier, because if you're doing spill response, you'll have a sample of the source. But what we have here is just groundwater samples from groundwater wells. So the signature is much more diffuse, and it could actually be mixed. So what we did, again, this is our partner company, Chemistry Matters. Luckily, they're forensic chemists, so we have access to all of that expertise. And these are the kind of tools you can use. This is fingerprinting of alkylated benzene. So on the left, we have groundwater well samples from known source areas. And our client had said that there was one area that they knew was a bit of an issue, and then there was another area that didn't make any sense to them. And so the top two are alkylated benzenes for it's the concentration of the various chemicals for the known source area for well number 1 and well number 2. And for well number 3, it's the unknown area. And you can see those fingerprints look very different. So there was diagnostic ratios that were done, and then we compared impacted groundwater samples on the right there, wells 4, 5, 6, and 7, to those source samples, and you can see that well 4 lines up with the source from well 3, and that's actually a condensate source. And then wells 5 and 6 look like the crude oil in well 1 and 2. And then well 7, it could be a condensate source, but there's a lot of non-detect, so it's really hard to tell. But at any rate, as our client, if they want to decommission this site, we really need to sort this out, because that condensate source is an active source, so they're never going to get rid of it if they're taking responsibility for it as part of, it's something that exceeds hydrocarbons. So human nature and the normal traditional way of looking at things, the regulator would assume that this is the responsibility of our client, when in fact it wasn't. Some other tools. So now this is another site, and I want to show again just how things can go sideways quickly. So this is a site that had 3 different sources of hydrocarbons on it. Again, a large facility site. And so when you had these, all were just elevated hydrocarbons, they all got included in the same plume. And when that happened, it looked like a huge issue. But when we looked at it, and when the chemist from Chemistry Matters looked at it, there were 3 different sources. So we had this normal diesel composition here, which a lot of you probably recognize. Those yellow dots are isoprenoids. So again, additional lines of evidence to back up the interpretation that was done on this site. So that's source 1. We've got normal diesel. Here's source 2. It's normal diesel with additional heavy hydrocarbons. That slope off to the right below the blue line is additional weathered heavy hydrocarbons. So that could be my client's responsibility. They handled crude on this site, so that could be their responsibility. That's in fact the only thing that could be related to their historical operations on this site. And then source number 3 was a gasoline signature. So now you might say, well, it's possible that the client over the course of the years used diesel and gasoline on this site, and that is a potential to look into. But the point is, we have 3 separate, very small areas of impact on this site, not one large area it's all hydrocarbons, it's all above guidelines, so it all gets included in the same plume. So you can imagine if you drew a line around all of the elevated wells on the site, you'd get a huge environmental liability on this site. Whereas if when you dig into the details, bring in the right experts, do your due diligence, and separate those hydrocarbon sources, you're left with 3 very small, manageable areas and a very small overall liability on this site. And it's questionable still whether that diesel and or gasoline can even be attributed to operations at the site, or if it's an off-site source. So answering questions like this become even more important on a large facility, because you're gonna think of having this issue with as many different responsible parties as exist at that site. If you've got 6 different areas on your site with third parties who have potential responsibility, well, go through this commingling exercise 6 or 7 different times. It's going to take a lot of work and a lot of data crunching. Good news is you'll have a lot of data from the years of monitoring that likely went on, but a lot of science is required. And what I find is what initially seemed like a big scary problem is actually not that bad. So just a couple slides left here. Does it pose a risk? So now you know what's background. You know that's not your clients. You know what belongs to a third party, another responsible party. You know that's not your client's responsibility. So now you know what is your client's responsibility. You can hone in on those finite areas, and you can determine, do they pose a risk? And so one of the things we really need to do, and I think Matrix is going to talk about it next, about modeling and CSM. So that's great. I'm not going to spend really any time on it here, other than to show this is modeling has gotten a lot better and a lot more affordable in the recent years. And this is, again, we're not an expert in this. We partner with another company, ProDelta Projects, to do our 3D modeling for us. But everything kind of on the bottom, the small little dots on the bottom of this site, are actually not our client's responsibility. Only that northwest corner actually had any source that they had to deal with. And so once you know that area, you can hone in on it and you can say, are there any receptors impacted? And then, well, I'm getting ahead of myself. We'll do this on the next slide. So here's an example. On the left, we have the original assessment, which looks like a huge area. So we got rid of all that noise and on the right is what was our client's actual responsibility. And you might think, that's great, that's a lot smaller. I think you could probably just dig that site up and be on your way. But north of that site, you see a wetland. So we thought, we really need to see if that's a sensitive receptor. We need to see if it's impacted. And lo and behold, it was below guideline. So we have exceedances right up against that wetland. And it's not exceeding, the water's not exceeding in that wetland. So then we thought, well, we just need to do some plume stability analysis, and that plume is actually stable. It's actually decreasing. So the plume is stable or decreasing, and the most sensitive receptor is not impacted. There's actually no risk on that site, meaning no further intrusive management or action is required. So you go from the picture on the left originally to the picture on the right, you've already made a huge improvement, But then when you look at it through, that's just why, so that you go from the left to the right just by doing steps 1 and 2, getting rid of background, getting rid of stuff that's not your client's responsibility. And then on the right, you start to say, okay, I know it's their responsibility, but does it pose a risk? And if it doesn't, there's nothing left to do. So that's basically all I really have to say. I just want to highlight again that answering those 3 questions on large facilities is difficult when you're decommissioning a large facility because of the many chemicals used, the multiple potential responsible parties, and the likelihood of commingling, and the large areas and amounts of data. So you have to make sure that you only do the portions of work that you're an expert at. So that's all I have to say. Thanks for your time. I know I'm at the end here. So
Thank you, Paul, very much. So next up, we have Sheila Luther and Galen Merritt from Matrix Solutions. I'm sorry, I didn't do an introduction for Paul with his bio, but I will do so in the panel. So Sheila Luther is a professional agrologist with over 20 years of experience with environmental assessment and research projects with a full focus on soil reclamation, contamination assessment, and remediation. Multiple years working on large facilities. And she's accompanied by Galen Merritt, who's a groundwater modeling specialist with Matrix Solutions with over 9 years of project experience. He's been primarily in source water protection studies concerning protection of municipal drinking water supply, but utilizes a suite of groundwater modeling software, including FeeFlow, Hydrus, VSMB, Visual AEM, and ModFlow. And so this has been actually quite an interesting example of kind of bringing in some more sophisticated tools for managing some of these challenging situations on these large facilities. So looking forward to the presentation. I will let you get to it. And we've been asked if folks could turn their cameras on, please, when they're speaking.
So Simone, I think I've been invited to share my screen, but if you could invite Galen instead, that would be our preference.
So here, you guys see this presentation?
We can, but just you need to change it to the
Yeah,
slide.
get it going.
Yeah,
Yeah, get it going. Okay, perfect. Just want to make sure. Oh, it goes backwards. Hang on. Yeah, hang on.
Actually, you can do it from the program. There's a display settings selection when you're in the tool that ESA provides. Up along the top there, Galen. Oh.
Hi, Galen, back where you were.
I've watched enough presentations, I can explain it.
Okay. I can just start it from here.
Yeah, just launch.
Yeah, okay.
And sorry about the earlier background noise. We left a mic on, so it's okay. Yeah, that button there, hit display settings. And then there's a display settings at the top there.
Oh, I see. Okay.
And switch to presenter view. There you go.
Super.
Okay, thank you.
There, it looks good.
Yes, so I think I'm going to start this off. So yes, we're taking the opportunity to speak a bit about some risk communication that we've been using for sites with large data sets. So I think it dovetails really well with Paul's presentation that he just did. Can you move to the next slide, please, Galen? Great. So we find that sites with extensive data sets can be challenging for clients and regulators to efficiently review this information and make informed decisions about the environmental management. So today we're going to review 4 case studies that show some advances that we've been trialing in risk communication. We're using some modeling tools, programming knowledge, and computational resources for these techniques. And our ultimate goal is to support our stakeholders to make more informed decisions where they have so much data to process and interpret. So I'm going to hand things over to Galen now to walk us through a few of the case studies.
Okay, so Hi, everyone. Before I really get into this, I want to stress that this presentation is not going to be your normal groundwater modeling or mass transport modeling presentation. I'm really more than happy to talk about all the intricacies of the whole process, but I'm not today. I'm not the point isn't to go over model domain selection, boundary conditions, or calibration targets for these case studies. What I'm going to do is give a brief overview of each site. And then show how we applied a groundwater flow mass transport model to understand risk. And the most important thing is how we conveyed the model output to the key decision makers so that better decisions can be made. Our first case study is located on the side of a ridge composed of interbedded shales and sandstones. It's got a history of chloride impacts and from its past as a produced water injection well. The sandstone units meet the classification for a domestic use aquifer or a DUA. And that make the various layers of sandstone throughout this site receptors of concern. So a very kind of schematic here of the conceptual flow model. If we cut a cross section through this site, like west to east, you can visualize groundwater flow. The majority of recharge infiltration enters the top of the, up on the top of the ridge where the soil and topography is conducive to infiltration. The recharge leaks through the small overburden of the first layer of sandstone, which is this first yellow layer here. I've got hydraulic conductivity as being the color of the cross section here. This recharge gets in that first layer of sandstone. Some of it seeps to the sides of the ridge, and another portion of it goes into the next layer and leaks into this shale unit, this lower conductivity unit. This pattern kind of repeats itself down to a middle sandstone DUA. Same process repeats itself with seeps out the side. A little bit of water goes out the side, but a lot of it still leaks down into this regional sandstone DUA where you have discharge to the creeks that run along either side of the ridge. So if we go in after a lengthy field program and investigating and drilling a lot of groundwater wells as well as soil samples taken at depth, we were able to collect enough field data that we could develop a three-dimensional interpolated chloride plume using a software program called Leapfrog. So we took that three-dimensional interpolated chloride plume and ported that into a numerical groundwater flow model so we could do mass transport. So this is just kind of showing the plume in 3 dimensions cross section here. And then the next thing is putting this into the cross section in the numerical flow model, which you can see has hydraulic conductivity layers as the color. So you can see this is kind of the overburden layer, this blue, down into this first sandstone DUA. This is our initial condition here. So the real thing, what we're trying to use this model to do is understand what potential impacts can occur, what can we do to mitigate those impacts, how effective will that mitigation be, and really the key point of this presentation is how do we visualize all this and convey it to those making the decisions. So the first piece I'm going to show you is what if we don't do anything? What if we don't have any mitigation measures at all for this site? So zooming in right now and looking strictly at the shallow sandstone DUA, I've in plan view here on the left, I've removed satellite imagery, sanitization and stuff. So this plot is showing this in plan view. It shows the footprint of impacts in the DUA. The color theme here is the highest concentration simulated over the whole model run for each XY location on this like kind of grid pattern here. So you can see, for example, that the highest impacts are around well 18.3 here, around 3,000 milligrams per liter peak if we look at the scale here. The aerial extent, so the size of this footprint exceeding guideline, is also calculated at 1,820 square meters right here. So given that each of one of these XY locations experiences a unique concentration over time, if we plot all of those concentration over time as a breakthrough curve showing the density, we can illustrate the spatial density of the concentration at each time step with this plot on the right here. So for this, for example, you can see the most commonly experienced concentration over time is following the yellow here over the site, whereas the highest concentration, these peaks up above 2,000, are experienced over a very small area. If we go down and do the exact same thing, but zoom our way down towards the middle sandstone, so our next layer here, you can see a much lower peak concentration, only hitting about 500 milligrams per liter here, on a much smaller impacted area, only about 964 square meters as opposed to 1820 in the previous one. in the DUA above it. And the spatial distribution of the peak, so this footprint, is much more homogeneous. It's kind of just a big blob, and the peak concentration is roughly distributed evenly over the site. This is just a result of this plume moving and dispersing downward through the flow model, and this is kind of illustrating that effect here. If we move all the way down into this deep sandstone, by the time the plume reaches there, all chloride concentrations are below regulatory guidelines, so there's not really anything to see here. So we've modeled and visualized the potential impacts if we don't do anything. So what can we do about it? So let's try to use this model to see what will happen if we excavate. A really common strategy is to apply an excavation concentration criteria. So that's, let's say we'll remove all material above a certain concentration threshold and replace that material with clean infill. So we're going to use the model to help us quantify for any number of any concentration criteria we want to test, how much material would need to be targeted for excavation, how much material would need to be removed in order to access that material, and how much it would cost, and perhaps most importantly, how effective would that investment be in mitigating impacts. So this chart and table illustrate 9 separate potential excavation scenarios. So nine remediation options or scenarios to varying excavation concentration criteria. So you have dig everything above 8,000 milligrams per liter, dig everything above 7,000, et cetera, et cetera. And these milligrams per liter, I guess I'll note, are equivalent groundwater concentrations. So the target volume here represents the calculated volume of soil at the site that's above this concentration. So for example, there's for this site, we've calculated that there's 330 cubic meters of soil that's above 7,000 milligrams per liter. This is represented by the orange line on the plot. So you can see that the lower the criteria, there's obviously more soil that that fits that. So this is increasing. What's also shown here is this excavation volume column, which is this blue line. Okay. And this is the amount of soil that you'd need to dig in order to access all the soil above criteria. This is translated directly into an estimated cost with this dotted line. So you can see this is plotted on the other axes here in terms of estimated cost, but in millions of dollars here. So you can see that this exponentially increases the more stringent the concentration criteria. So with plots like this, you can really convey the diminishing returns. You have to excavate potentially more and more as the concentration criteria decreases, not just to remove the soil that's actually above criteria, this orange line, but primarily just to be able to gain access to that dirty soil by digging up all the clean soil above it, which is what you would have to dig for that blue line. So harnessing improved computational resources, so this is cloud computing or in-house computing resources that we have, to programmatically set up, execute, and run all of these excavation scenarios in parallel. And this was done overnight. What you see here is that these are peak breakthrough curves for each scenario to see basically what good it does. It's the effect of this remediation on reducing the peak breakthrough curve at our key receptors. So you can see, for example, in the shallow sandstone on the left, that even the most expensive 1,000 milligram per liter, very, very expensive, won't result in peak concentrations getting below regulation guidelines, but it can significantly reduce the duration that exceedances are experienced. So that, I think, is a really good way of looking at that plot there, where you can see, okay, wow, this 1,000 milligram, I mean, things are cleaned up by 2040. It's not so much by, if we didn't do anything, it's going to be there for a while. In the middle sandstone DUA over here, you can see that actually the 3,500 milligram per liter criteria, so this one there, gets our breakthrough just below the regulatory guideline of 250. So and then you can also see that even doing a relatively small dig, you still get a pretty good reduction from 500 to 400 in terms of that. And you can also see the duration, basically the distance between where one of these lines crosses the dotted line and where it crosses it again. That's the duration of exceedance, which can all be calculated and reported on. So if we look at that 3,500 milligram per liter excavation scenario and do those density plots that I showed previously for the base case. So the idea here is showing this is what happens if you do nothing for the base case, but if you excavate all soil greater than 3,500 milligrams per liter, you get a good reduction in the peak, and in the peak, as well as a general reduction in the spatial density in the peaks. However, the size of the footprint that you excavate doesn't really change much because you're just targeting these hotspots around well 18.3. Around those really hot spots, but the peak concentrations experienced there still are reduced. So you can kind of see this kind of reduction there. So what I've just gone through here are a few novel means of illustrating what the model's telling us, not just in terms of like your basic concentration time breakthrough curves at receptors, but looking at this more in a spatial context as well as an aerial density sort of context. But we have something else here. And what if we took this a step further and we added user interactivity to the figure? So this next one is a totally separate site. This is another case study here. There's a well-established plume at this site that's moving eastward through a DUA. We have a working transport model that simulates this migration. So for this site, the only potential remediation measure that's practical in any way is recovery wells. But how many wells to put in, where to put these wells, how much to pump them, and for how long to pump them, we don't really know what's best. So we tried a suite of pumping configurations and ran them through the model. The model results were post-processed and presented in interactive HTML that allows the user to scroll through time and directly compare one plume footprint to another. So I'm going to test drive this here, and hopefully this works out pretty cleanly. All right, hopefully you guys can see this. So this is that HTML plot here. So the idea here is that we're looking at the plume in plan view at time 0 right now, and the user can select this. This is an interactive HTML document, and the user can select this and choose to view one scenario versus another. So if we look at only the base case and simplify this, this is the movement of the plume footprint over time, moving west to east over time. If we wanted to compare, say, the scenario if we sited 5 wells and pumped them 200 meters cubed per day, we could compare the two and see the difference. Here, I'll pick a more contrasting color. But here's 10 wells for 200 meters cubed per day, and you can see the effect that that siting 10 wells has at reducing the plume footprint over time as you move it. On the right here, you'll see the size of the footprint is calculated for each time step for each scenario. So you can see at any given time, how much footprint remaining you have. So as far as decisions that are made and when you want the site to be cleaned up and what's acceptable and all of that, this is a great tool for engaging the stakeholders to understand what we're looking at and getting everybody on the same page. So I'll go back here. Okay. So moving on to the next case study here, I'm just going to give another example of this kind of interactivity to show our model results. I guess the other thing I forgot to mention about these interactive HTMLs is that they are completely standalone. They're coded up using a combination of Python and JavaScript. The point of why I'm telling you this is that they can be viewed with any web browser, and you can even send them, and they're generally very compact and small and easy to use. And like you can even load them on your phone. So it's a really, really nifty portable tool to share your model results with clients and or regulators. So going back to show this for another site, I built an interactive HTML to visualize plume migration in 3 primary geologic units on site. So this is a site that has a peat layer, underneath that is a clay, and underneath that is a bedrock DUA. There's been a historic chloride release in that peat. We're really concerned about the DUA receptor and a well that's located off-site. We're focusing right now just on a base case or no remediation scenario focus here. So if I demo that guy here, getting faster at this as we go. So this is showing the plume at time 0 here. This is plan view in the peat, and then we've got the clay layer right below it, and then the bedrock. So this is kind of showing the plume. I can zoom in a little bit here so you can see that's kind of the shape of the plume. Concentration, this is all satellite imagery removed. Concentration contours are here on the right. And you can kind of scroll through time and visualize how the plume moves over time, and in the various units. This red dot here is representing the location of the highest concentration being experienced in the bedrock DUA. And obviously, because groundwater is moving and the mass and the chloride's moving, that highest concentration will move over time. So you can see it following kind of the center of that plume. The location of the well that we're concerned about is represented by this blue dot here. The plot below here is again showing that spatial density that I was talking about in terms of what concentrations are experienced over what area. So you can see, for example, here, if we move like kind of like to the time of peak around the peak here, it's only, you can mouse over this and see that it's a very, very small area. Well, relatively speaking, only about 400 square meters of DUA like footprint is experiencing this peak. Whereas around that time, the more frequently occurring or the more commonly experienced concentrations are down here in the 70 to 100 year range. And you can kind of see that through this whole plot. And we'll also know that I've plotted the well receptor as well here, showing that for this particular site, there's not, we aren't simulating much in the way of breakthrough or any sort of issue towards this well, but there are noted impacts to the DUA directly on site. And this is kind of what this model is telling us. You'll also see that the area of the footprint in each layer for each of these concentration contours is being calculated and illustrated over time. So you can see, for example, right here, if we look at the bedrock, you'll see the plume breaking through into the bedrock. The area of it is growing. We're at 1.52 hectares now above the 120 line. And it's growing and growing, and then it's starting to disperse and come back down as we move into later time. So this is like a great visualization tool that is very portable and is a great way to illustrate what this model is telling us and illustrate that to those that are making the decisions. So I'm going to so that's it for me. So I'm going to get Sheila to take back over, pass the torch to her, and she's going to use this kind of interactive figure to demonstrate some work that we've done towards representing a very key process in sulfate transport.
Okay, so Galen, you can just advance the slide.
Yep.
Okay, so we've become interested in looking at the problem of sulfate transport in a calcite or calcium carbonate, in other words, rich environment. And this relates to some of the information that Paul was presenting and will relate to the subsequent presentation after our presentation. So this topic can be related to, the reclamation of sulfur base pad areas, which are common. Historical sulfur base pads are common in the sulfur gas plant situation, and dilute sulfate plumes are common in these sour gas plants in Alberta, where there's been historical handling and storage of elemental sulfur. So once oxidized, elemental sulfur is converted to sulfuric acid. So you can see that in this equation, that sulfuric acid is one of the contaminants we're a little concerned about. In a calcite-rich environment, it interacts with the calcium carbonate, and you can get precipitation of gypsum. So due to this dominant reaction that can be occurring at our gas plant sites, the sulfate doesn't behave like a conservative contaminant like chloride, and it becomes necessary to understand these processes in order to really predict the transport of sulfate in the subsurface. So at lower pHs, you'll get more dissolution of the calcium carbonate and more potential to precipitate gypsum. And some sulfate will precipitate out and some will remain dissolved. So we're going to speak a little bit about our attempt to model this. It becomes tricky because you have mass transport happening as well as the precipitation dissolution reactions. So we've coupled a mass transport model with a geochemical speciation model to come up with a way to predict how sulfate will behave in these scenarios. So in between the mass transport model steps, a geochemical run is being conducted at each model node, representing a portion of the space. And this determines the amount of gypsum precipitation. And the amount of a certain amount of gypsum is precipitated at each node stored in an array. And at later times, the dissolution of gypsum occurs as clean groundwater flows through. So we look at that as well. And so we're going to show another interactive HTML to depict this information. Alrighty, so with this scenario, we have three different types of scenarios that are modeled. We have one that's accounting for no precipitation dissolution, another that looks at precipitation and dissolution, and then one that only looks at precipitation. So if we start with no precipitation or dissolution being modeled, Galen will show that that's how the plume behaves. And you see a breakthrough curve there that's at the observation point that's shown on the graph to the left. And so, you know, this is just that modeling sulfate as a conservative contaminant. Then we'll try just showing an instance where the precipitation is occurring. And what you'll see with this, we have a different breakthrough curve. It's the red one to the right, and the peak is slightly lower than the blue peak. And you'll see in the plume to the left that that red hotspot disappears right away. And so this is an interesting thing that we notice with these types of sulfate plumes. Now, there's a third scenario where we look at precipitation and dissolution that we can depict with this example as well. And so as that's occurring, we get a different breakthrough curve that's intermediary between the red curve and the blue curve, and that's the green curve. And so essentially what's happening there is initially, we do get precipitation, but later as water's flowing through, the gypsum slowly dissolves into the groundwater flow system, and it results in a lengthened tail of the breakthrough. The area between the blue line and the green line will eventually be equal, like the area under the curve, because the amount of mass moving through the system will be the same, but it'll be distributed differently temporarily through time. And so these examples help us to understand better how these sulfate plumes will behave in the environment. The exact magnitudes of these curves and the timeline will depend on the nature of the source and the overall conceptual site model. But commonly in these calcite-rich environments, you can get very high sulfate concentrations at the source from the sulfur base pads, sometimes in the tens of thousands ppm, but they're quickly dissipated through the reaction with calcite. So I'm going to pass this back on to Galen to just cap off our presentation. I'm not sure if we lost Galen there for a minute. While we're waiting for him, I'll maybe just continue to speak to the presentation. So essentially what we wanted to depict, oh, you there, Galen?
Yeah, I was muted by the organizer. We're good though. Can you guys can see the screen here? Hopefully you can see. But so the main piece here, what I'm trying to hammer home here is that peak breakthrough curves. There's more than just that to look at out of model output. We can look at the area of impact. We can calculate volumes of impact. We can look at the spatial distribution of impact. We can calculate the duration of impact. We can illustrate these temporal things through interactive HTML diagrams. With increased computational resources and a basic programming ability, we can convey model results to stakeholders transparently, digestibly, and quickly. It helps to get everyone on the same page. The whole idea of user interactivity as a means of engagement, I feel, is extremely promising. The other thing is that this kind of tool can also be used to just illustrate a key concept, such as gypsum formation and/or dissolution. The whole point here is that we want to maximize we want everyone to maximize their problem understanding so that optimized decisions can be made. For me personally, my next application for this, or the big next step, is to attempt to write some sort of optimization algorithm for optimizing excavation scenarios and/or pumping scenarios. So yeah, here is our contact information. Thanks for listening.
Wonderful. Thank you, Sheila and Galen. So next up, we have S2 Environmental, and Aaron Kempen and James Freeman will be presenting. If you can, please, cameras on, and we need to make sure that both of those individuals are able to present. give a quick intro for Erin and James. So Erin is a hydrogeologist with S2. She has over 15 years of regulatory industry and consulting experience. James Freeman has over 30 years of environmental and hydrological consulting experience, much of it based in Western Canada. He's currently program director for S2 Environmental JV.
Oh, sorry, Simone, how do I see where it's, if it's sharing what I needed to share?
Are you sharing?
It says I am sharing.
Okay, are you in presentation mode?
Bottom
right.
Yeah, sorry, it's just, this is in the way. I'll just move this out of the way here.
There we go, and then we can, there we go, that looks great, Erin.
Okay. Okay, perfect. Thanks. All right, so good afternoon, everyone, and thanks for staying for the last talk prior to the panel discussion. My name is Erin Kempen. I will be presenting this talk for the team, but I'm sure James can chime in on any questions as it goes along. So first, as our overall agenda, we're going to put together the problem of decommissioning sulfur base pad into the regulatory environment in Alberta and highlight some of the regulatory data gaps. And then I'll get into a specific example with the Balzac gas plant and go into the details of where we are on the remediation work and some of the challenges and findings noted at the site today. And then lastly, I'll go over some conclusions, recommendations, and hopefully there's a good discussion to follow. So decommissioning older gas plants is likely to represent one of the most unique industry and regulatory challenges, as they have decades and decades of production, and in some cases expansions or adjustments during operation. So managing the layered contaminants of potential concerns within layers of upgrades or expansion can create challenges that will need input from both industry and regulators to ensure successful remediation at these sites. Several dozen or so sour gas processing plants in Alberta recovered sulfur by pouring molten sulfur onto these large sulfur base pads. And the molten sulfur cools and it forms these large blocks like the ones seen above. These base pads can be hectares in size and can form a large part of the decommissioning activities. Decommissioning work for some of these large sulfur base pads has just started, and it is highlighting some of the data gaps and regulatory uncertainties. The main guide for decommissioning sulfur base pads or remediating sulfur impacted soils in general is the guideline for landfill disposal of sulfur waste and remediation of sulfur containing soils in conjunction with the Tier 1 and Tier 2 guidelines that you're applying at your site. So Sheila already kind of went over this. So I will try and make this quick, but elemental sulfur will break down in the presence of oxygen and with the help of microbes into sulfuric acid. And over time, this can lead to acidification of both soil and groundwater. The guideline is very clear that all soils impacted with greater than 4% total sulfur need to be hauled off site to an appropriate waste management facility. It's not clear in the guideline where the greater than 4% total sulfur comes from. And as far as we know, there's been very little regulatory appetite to treat higher concentrations of total sulfur on site. So once the sulfur impacted soils contain less than 4% total sulfur and greater than 500 milligrams per kilogram elemental sulfur, there is the opportunity to amend the remaining elemental sulfur on site. And amendment is encouraged in the guideline with the intent to reduce the volumes of soil going to landfill. And no remediation is required when the soil concentrations, the elemental soil, is less than 500 milligrams per kilograms. So when considering an amendment, the guideline states that limestone must be applied using the formula shown below, and that you must include the acid neutralizing capacity of the soil. The soils for much of Western and Central Alberta do have a high natural buffering capacity, and that needs to be accounted for within any amendment project. And so as I'll discuss in later slides, a high natural buffering capacity could actually mean that no lime is required to mitigate the breakdown of elemental sulfur. And applying lime without considering the A and C of the soils could lead to basic pH and potentially form gypsum crusts on the soil. This also, again, sort of raises the question of where the 4% total sulfur number came from, and if site conditions are good, should it be possible to leave greater than 4% on site with the lime amendment? Further research on how to determine what level of impacted soil should go to a landfill versus what can safely be treated on site needs to be completed. And lastly, irrelevant of the concentration of elemental sulfur that can remain on site, the guideline really doesn't address potential sulfate loading in groundwater. And this raises an important questions in regards to how we're proposing to address sulfate loading in groundwater, including things like what density of wells do we need to confirm sulfate plumes? What are the monitoring timeframes do we need, especially if we're looking at amendments? So further work is needed to understand the whole picture in regards to final decommissioning activities that need to be completed at sulfur base pads to ensure no ongoing environmental impacts remain in the soil or groundwater, and to provide some regulatory certainty to operators. So this slide from Sheila and Simone sort of shows how some of the science could be applied to allow industry and regulators to more easily account for site-specific conditions. So our case example for this presentation is the Balzac gas plant. The plant started operations in 1961 and continued processing gas until 2011 when remediation activities began. And I've highlighted in red sort of the approximate outline of the sulfur base pad at the BGP. And in orange, you can see sort of the approximate outline of the site to kind of put the problem into scale. While I've only highlighted the sulfur base pad, it's really important to keep in mind that we know other areas in the plant also have sulfur contaminated soils above the 500 milligrams per kilograms elemental sulfur. So specifically for this case example, we're focusing on the east sulfur base pad, as this is the first area where we've removed all the soil with greater than 4% total sulfur. And there's approximately 0.1 to 0.3 meters of soil that exists within the amendable range. And what we really noticed as we reduced down to lower and lower concentrations of elemental sulfur was that the pH of the soil quickly moved into the neutral range. And this led us to start thinking about what potential impacts to soil and groundwater would be if we amended, as the reason for adding lime is to mitigate depressed pHs, and those were notably absent at less than 4% total sulfur for the site. So before we dig into the sulfur data, a very general CSM is probably helpful for context. The BGP is situated in a classic prairie evaporitic environment, and shallow groundwater is naturally characterized by high sodium sulfate concentrations. The shallowest groundwater bearing zone is comprised of the till and weathered bedrock, and this zone is not considered a DUA due to high TDS that's characterized by sodium concentrations up to 12,000 milligrams per liter and sulfate up to 38,000 milligrams per liter. So the shallowest DUA on the site is actually the upper sandstone groundwater bearing zone, and it's found at approximately 15 meters depth. The nearest water body is McDonald Lake, and it is situated along the western edge of the site. McDonald Lake is a shallow evaporitic lake with no perennial water courses flowing into or out of the lake. And it's also characterized by high TDS, up to 7,000 milligrams per liter, and that includes high concentrations of sulfate of 4,000 milligrams per liter. So we evaluated the background concentrations of sulfate in the shallow groundwater bearing zone, and shown here is sort of a box and whisker plot outlining the background sulfate concentrations in groundwater. You can see the median value is 3,000 milligrams per liter. The upper quartile is 13,000 milligrams per liter. And the upper whisker that we have defined, as you can see on the left, is 31,000 milligrams per liter. Evaluating the background sulfate concentrations allowed us to feel confident that the sulfate loading is unlikely to be of concern, particularly when total sulfate concentrations are less than 4% at the site. So this is just sort of a rough schematic of how we conceptualize the East sulfur base pad. And on the left is the schematic during production when the sulfur block was sitting on the surface of the soil. The marketable sulfur was removed shortly after decommissioning started, and by winter of 2020, we'd removed up to 1 meter of soil with greater than 4% total sulfur. And based on the test pit data, we have approximately 0.1 to 0.3 meters of soil that's within the amendable range. So there's been a lot of ongoing data collection throughout time at the sulfur base pad. And when we noticed that the pH was moving into the neutral range or even into the slightly basic range, we wanted to compile all of this historical data and evaluate the natural buffering. So most of the soil data came from a very large 2015-2016 soil sampling program. And there are two things to keep in mind. The historical data had a very large bias towards samples with higher concentrations of total sulfur. And some of the lower total sulfur values that were collected soil samples had much higher total sulfur concentrations sitting above it. And thus the data needs to be reviewed in that context, that there was likely a significant amount of sulfuric acid leaching downward. What this figure does show, though, is that the pH of soils with greater than 4% total sulfur. So all we plotted here is all of the pHs and all of the greater than 4% total sulfur values we had at the East sulfur base pad. And what you can really see is that approximately half of the samples already had a neutral pH, even at higher total sulfur concentrations. We have this one sort of residual point in red that looks like at the East sulfur base pad, there might be some small greater than 4% total sulfur remaining. But again, this was a historical sample, and what we suspected that there's actually slight differences in surveys that make it look like it's still there, even though we've probably already hauled it off site. Irrelevant of whether or not it's there, this sample is above 4% and is almost within a tier 1 value for a pH of 6.5 and within our background pH value of 5.84. On the last slide, we showed everything that had greater than 4% total sulfur, and this slide shows all the data within the amendable range. So in 2015, 2016, all of the data was focusing on where is the higher concentrations of total sulfur, and in 2020, when we were looking at pine lime, all of our data was kind of focused on where are we getting to that close to that 500 milligrams per kilograms data. So there is sort of kind of a bias you can see in a lot of our data set towards the lower end of the samples. What is really important to look at when looking at this slide is that all of the samples are within our background ranges, and all but 2 are within a neutral pH already. And the 2 samples that are sitting up around that, in between that 3 and 3.5 on the far right, again, those are historical samples and likely had higher concentrations of total sulfur sitting above them. So when we started to want to look at what is the buffering on site, it was important to keep in mind that natural buffering for acids is dominated by calcite and dolomite, and thus the calcium carbonate equivalency is a good measure of the buffering capacity of the system. The CCE measures all carbonates within a soil sample, and therefore the assumption is that siderite is only present in small amounts, as it really won't buffer an acid. By graphing the pH versus the calcium carbonate equivalency, we can visually see the inflection point right about this 3.4 here, where the pH of the soil is changed from being slightly acidic to being within the neutral range. So what you can see is that when you're on the right side of that 3.4 line, the samples have a lower amount of calcium carbonate equivalency, and you can really start to see the depressed pHs in some of these samples. However, when we move towards the left of the line, the samples have a much higher calcium carbonate equivalency, and they have higher pHs. In fact, almost all of them are within the background range, and most of them within the tier 1 value. So the CCE measures all carbonates in the systems, but only dolomite and calcite will actually effectively buffer for acids. Siderite, which is also a carbonate mineral, isn't very soluble, and it won't provide any measurable buffering in the system. So this graph is showing the pH and the percent carbonates present in the system from XRD analyses. Again, as part of the sampling bias, we only had 3 samples that were submitted for XRD with total sulfur concentrations with less than 4%. We plotted the carbonates. Oh, sorry, I didn't mean to do that. We plotted the carbonates measured in the system for ease of viewing, but keep in mind that other minerals, particularly quartz, are present in the system. The 2 green and blue samples that have the neutral pH range that you can see here, they have high amounts of calcite and dolomite, and no siderite was present. And then the 1 mustard colored sample that does have a depressed pH has no calcite and dolomite remaining, and only a small amount of siderite was present. And this sample was sitting directly above a soil sample contaminated with 60% total sulfur, and the natural buffering capacity was likely depleted from buffering the amount of sulfuric acid leaching downwards. So in this graph, what we did is we basically took the AER formula, so the theoretical amount of lime that would be needed using the AER calculation, versus the calcium carbonate equivalency and the total sulfur of the samples from the sulfur base pad. And what we can really see here really easily is that every point plots above the mustard line, and therefore theoretically has enough carbonates present to buffer the release of sulfuric acid. And this really highlights that the application of lime is not needed at the BGP for amendment, and could actually lead to net negative impacts such as basic pH or gypsum crust. So we use the total sulfur values in doing this theoretical calculation of that mustard line, and not the elemental sulfur values, to ensure the theoretical amount of lime was as conservative as possible. And had we completed this equation with the elemental sulfur, the amount of lime needed would be significantly lower than what is currently plotted. So again, you can see the bias off to the left-hand side of samples with much lower concentration of total sulfur. And thus we plan to confirm the natural buffering with a large sampling program across these East sulfur base pad that I'll discuss in the next slide. So we're planning to do 2 levels of data collection and monitoring as part of our non-lime amendment. First, in order to confirm that the soils with total sulfur concentrations near 4% have a high acid neutralizing capacity, and the pH of those samples is within or close to a neutral pH, we will be doing a tight sampling grid. And you can sort of see the sampling points that we're going to be proposing. They're the red dots that are highlighted. Second, we obviously, if we think that we do not need to buffer the soils with lime, we obviously need to do some monitoring to support our hypothesis. So we're going to be proposing ongoing monitoring for a period of 2 years. And you can see the larger light blue squares are the proposed soil monitoring points. And then the smaller dark blue triangles are the proposed groundwater monitoring locations. The natural buffering capacity of soils has been previously pointed out, and this figure shows that where most of the sour gas is found, there actually is a high natural buffering capacity in the soils. At the BGP in particular, John Fennell completed his MSc thesis on the sulfur isotopes at the site, and he concluded that while some sulfate was being released into the groundwater from the sulfur base pads, it was well below the natural background range of up to 38,000 milligrams per liter. And additionally, a geochemical study has already been completed that highlighted the natural buffering of the soils on site and suggested up to 20% total sulfur could be left in place with the lime amendment. What is new is that we're one of the first sites to remove all of the contaminated soil with greater than 4% total sulfur, and to be evaluating the feasibility of a lime amendment. So for discussions points, there are areas in the province where little to no lime amendment will be needed at less than 4% total sulfur. And addressing the potential impacts for sulfate loading in groundwater is a key piece that is currently left out of the guideline, and this includes what should be the requirements for monitoring in terms of the appropriate number of wells, the timeframes for monitoring. Currently, the monitoring requirements for soil and groundwater are all related to achieving a neutral pH, and it doesn't really address sulfate loading or account for soils with a neutral pH without a lime amendment occurring. Lastly, if the intent of the guideline is to reduce the volume of soil going to landfill and amending where possible, is it worth looking into leaving higher than 4% total sulfur concentrations on site and amending? And what are the concerns with this? And is it really total sulfur that's the best number that we should be using in regards to what needs to be hauled or what can be left on site? Remediating sulfur base pads, particularly at older sour gas plant, is likely to form a huge part of remediation activities. And the guideline was developed during a time when most operators and regulators were likely concerned with managing operational sulfur base pads and the associated waste management facilities. And I think it was sort of assumed that a lime amendment would be needed for any soil with sulfur concentrations between 4% and 500 milligrams per kilograms elemental sulfur. As more plants with large sulfur base pads move towards final remediation and reclamation, it is critical that there's a regulatory vehicle to discuss site-specific conditions and provide timely guidance on acceptable methodologies monitoring to evaluate the best path for closure. These discussions need to happen while remediation is ongoing and cannot be addressed when applying for regulatory site closure, as there is a significant amount of time and work and money that goes into remediating these base pads. And it's really important that operators and regulators to agree on any proposed remediation work before it begins in earnest. So putting together this presentation was a group effort, and in particular on the S2 team, we'd like to thank Amber Kobes. She did a lot of the data crunching and worked on most of the figures shown in this presentation. And we also really need to thank CNOC, particularly Greg Denham and the Balzac Abandonment and Reclamation team for allowing us to present the Balzac gas plant as an example. So the picture on the left is the Comet Neowise, and this photo was taken by one of the co-authors, Lawrence Talisi. So if there's any questions, you can feel free to ask, or alternatively, my email information is up there. And I thought that while addressing any questions, this funny meme would entertain everyone. And I have to say, for my family, too many of these is proven true, with number 5 being my favorite.
We do have a couple of minutes for questions on this one. So if anybody would like to jump in, by all means, go ahead, please. Just post your question in the chat.
Not clear to me where the chat is. Is it obvious on here?
Here we go. We got one, and I think it's in the it says type message here. Somebody, a little bit of a microphone. Okay, so we have a question from Sheila. In the sour gas area, is it likely to get this high of natural groundwater sulfate?
Sorry, I think you cut out for 1 second, so I missed part of that question.
In the sour gas area, is it likely to get this high of natural groundwater sulfate?
Well, I think in the area we are, it really is. Like, it's a very highly evaporitic environment, and we do see like the high natural sodium sulfate concentrations. So I think that's somewhat unique perhaps to the Balzac gas plant, and that might not, and I think it doesn't, I know it doesn't exist at other gas plants, but here, everything that we looked at for the background, all of the data that we compared, the sulfate was quite naturally high.
Yeah, it always puzzled me why they built gas plants on top of hills for the most part, and had a pipeliner up in Lloydminster that said, well, we got sick of filling in sloughs. So, but apparently this site, they did want to build it across Highway 2, and they decided, but the farmer wanted him to build it there because he couldn't use the land anyway. So,
yeah.
Good. Okay. Well, if that's it, we will wrap up. Please stay in the room as we'll be starting our panel discussion at 3:20. If you can get the panelists to join up, that would be great. Thank you.
Hello, everyone.
Hello.
I can hear you, Sheila. Paul?
Hello.
Awesome. Wes? Sheila, it looks like you have a little sunshine.
Yeah, I got a really bright sun happening. I could go take the blind down, but I don't really want to, you know? I could. Should I? Oh, it's a little awkward. I think there's going to be more clouds soon. I like the natural blind.
Right.
Can you hear me now?
I think that's Wes. Yes.
So James, no flies in the office?
No, I was in Dollar Store the other day and I was thinking of getting a plastic one, but I couldn't find an appropriate one. But if there is, red hair color.
We'll let you know though. We won't be
Okay.
Kamala.
No.
Oh my gosh, I died laughing. I can't believe I didn't see that before we met, but yeah. And apparently there was a Joe Biden raised a lot of money with a photo that with a fly swatter. All right.
So you're gonna open up mics within the session, or are people gonna have to type out questions?
I think that they should type them. I think I'll encourage them to type.
Okay.
Can our tech weigh in on the feasibility of turning on a mic if somebody needs?
I do have the ability to turn on people's mics, but we have 86 people in the room, so it might get a little bit hectic if we do that. I think the best way is probably to just have people type them in the chat, but I mean, if somebody does have something important to say, I can definitely turn them on.
I have an idea. There was a raise hand option, so perhaps they could raise their hand and then you could turn that mic on. I don't know.
Yeah, that's possible. Yep. If we want to do them one at a time like that, for sure. Yeah.
I don't see the raise hand button.
Yeah, we don't have it, but it was there before
Okay,
before
I was actually just informed no raise hands. Just type the chat, but type in the questions, please.
All right, let's keep
Joe heard that and said no.
Okay.
So we are live, so it's 5:20. Whenever you want to get started, go ahead. Or 3:20.
Okay. Okay, so this is a bit of a unique opportunity that we have here at RemTech to have a panel discussion. It was something that we've been sort of leading up to in the session. So if you weren't present as an attendee for the previous sessions, you can always go back to the presentations. They'll be online. We'll be referring to them somewhat. But really, the goals of the panel and this session on this large facility management, you know, we're really looking to dig into liability associated with these sites and how to remove some of that liability just from a provincial perspective. What is the incentive that owners have for dealing with these sites? How are we aiming to get to closure for a number of these sites that are on the landscape? And then specifically around the innovation opportunity. This goes to innovation within companies, with entrepreneurs, and with in the research and innovation space specifically. We have technology developers in the province that are looking for opportunities to bring their skills to the work that we do and many others do as well. Some of that silo removal is a way that we can move forward in the space. So before I take up too much time, I want to leave a lot of discussion time for the panelists. Let's do some introductions. So we have on our stage now, I am seeing a blank slide. I don't see the panelists.
They're all here.
Okay, I'm just not seeing them. Good. Okay, I'll just change my screen. Okay. So Paul Field-Brandt has cultivated an increasing specialization in developing and executing attainable closure plans for contaminated sites over the last 20 years. The motivation for this work is drawn from a desire to return as much land to productive use as possible. To that end, he co-founded StatViz Analytics Inc. to develop user-friendly software tools to understand and communicate environmental data. He also co-founded Precision Liability Inc. to provide a cost-efficient process to eliminate environmental liability for the benefit of his clients and the land. That's Paul Field-Brandt. Sheila Luther is a professional hydrologist with over 20 years of experience with environmental assessment research projects with a focus on soil reclamation, contamination assessment, and remediation. Her work experience includes contaminated soils assessment, remediation, pre-construction, post-reclamation assessments for oil and gas industry sites, environmental monitoring, literature reviews, tech transfer, and research on soil water contaminant interactions. She's with Matrix Solutions. James Freeman has over 30 years of environmental and hydrological consulting experience, much of it based in Western Canada. He's program director for S2 Environmental JV. So we have 2 soil scientists and a hydrologist. So we should have some good discussion there.
Hi, Simone, it's Joe. We're going to try doing the hand raising, and the tech's going to try doing the turning on the mics. We don't know how well it'll work, but we're going to try it if people want to try that instead of typing in questions. We're going to try.
Okay. So for those of you that have your window, if you can locate the hand raising button, then that will allow you to weigh in verbally, and that will help facilitate our discussion. So last but not least, Wes Funk, new to the session. He's the founder and principal of DXD Consulting Inc. He has over 25 years of experience delivering advisory services to energy, infrastructure, and mining projects around the world. During this time, has developed several regional and global scale enterprises focusing on decision analysis, risk management, sustainability, and strategy and policy development. Central to these efforts has always been sustainable development, or as is more recently favored by investors, environmental, social, and corporate governance, or ESG. So that will be a little bit of a theme throughout. So we'll be asking 3 questions. Audience, welcome to weigh in. I'm sorry, but I'm just not seeing the, I'm not seeing the panelists, and it's difficult for me to be able to moderate this. So sorry, can somebody jump in? And there we go. Okay. All right. So we're going to be asking 3 questions, and okay, now I've got it. Okay, asking 3 questions, and each person will respond at a time. Feel free to jump in if you want to comment on something that somebody else said. So the first question really related to this question of data analysis, scientific interpretation, conceptual site models, and these tools that we've heard about in the previous presentations. How are they used for supporting stakeholder communication? And further, how do intrapreneurship and entrepreneurship contribute to development of these tools and approaches? So this is something that the intrapreneurship and entrepreneurship, so intra being within companies, people with specialized skills being brought in to support projects like we had with Galen as an example. I thought that might put a bit of a twist onto the into the discussion for our panelists. So let's go ahead with Sheila first.
All right, I think you can hear me. Yeah, so I did want to kind of showcase again the presentation that we just completed, which was entitled Advances in Risk Communication for Large Data Sets, as you referred to, Simone. And we found those interactive HTMLs to be a great new way to communicate conceptual site models. Idea being is that we can look at multiple remedial options and cost evaluations and quantify the future potential risk to receptors in a whole bunch of scenarios. So having worked in this for a long time, it used to be, oh, you know, maybe we can do 3 scenarios or whatever, but now we can do, you know, tens of scenarios, and that modeling and calculations allows us to look at the liability costing as well, using computer programming instead of like me manually doing it in some sort of spreadsheet or something. So these tools are now accessible within days or weeks of work, instead of, you know, it might have taken historically some maybe months of work and, you know, not as many options. So that's great. A couple of other things I just wanted to mention are geographic information systems and all the advances that are happening in that, right? So all sorts of, we see this every day, right? We go on the search the internet, or, you know, use Google Maps or whatever. There's just so many options now available to us. What I like at our fingertips as practitioners, we have all kinds of digital mapping information, be it facility footprints, wet areas mapping, bedrock geology, caribou protection zones, all of that available and potentially integrated. Certainly I have access to that, so it's pretty fantastic. And we're able to search you know, this data for information. And then one other thing I just want to mention is the digital transfer of information from field to office to field. So that's becoming more and more readily available, be it things like you know, GPS mapping of our sites, the borehole logging, things like downloading all the data as well into analytical requests, UAV imagery, EM surveys, etc. So yeah, that's just another thing that I want to mention, that we've seen a lot of recent advances in compared to, say, when I started out handwriting my chain of custodies and so on.
Great. How about you, Paul? Tools and entrepreneurship.
Yeah, I mean, in terms of the tools, my perspective is if there's any stakeholder at the table who can't ask meaningful questions, then we haven't done our job as scientists. That means whoever has the least amount of education and understanding at the table, everything has to be at their level. So I mean, typically this really means maximum grade 8 level when you're communicating your information. And so tools, obviously, visual tools make this much easier. It's much easier to communicate in a way that everyone can understand with visualization tools. And when we do that, we find that every stakeholder at the table can ask meaningful questions, which means that they can be bought in. Because if someone doesn't have a voice at the table, they're not going to be bought in. And if they're not bought in, your project's not going to go forward. So incredibly important that these these scientific concepts are communicated simply and visually, so that everyone can engage, whether that's landowners, First Nations, right up to right up to your subject matter experts.
What?
Sorry. I think I've got 2 minutes. I'll try not to overspeak it. When it comes to data management, innovation, entrepreneurship, intrapreneurship, these things all tend to circle around in one big constellation. We are the center of that universe when it comes to things like remediation. When I look at data, I can't help but agree with Paul on so many fronts, but in this case, the value of collaboration and the ability to give not just insight, but voice to stakeholders, whether they're investors or landowners or regulators or peer companies. It's that voice is pretty critical. And where I see data democratizing is when we start sharing those data, start collaborating around those data, we start seeing the ability to promote and advance areas of remediation and science that we wouldn't otherwise have done. Think about an area-based closure campaign. If only one company participated, not a lot of insight. 10 or 12 companies participating, lots of insight. If we hold those insights simply to cost data, that's one thing. But what if we start sharing our background soil conditions? What if we start understanding mutually what kind of groundwater conditions we're observing and using those insights to start driving towards other endpoints and communicating that not just amongst peer companies, but then obviously with the regulators that you need support from, but also then the landowners, because these landowners that we're talking about, it's not just a landowner on an ABC campaign, unless they're an incredibly wealthy landowner with a lot of land. So there's a lot of landowners that need to engage. And that's where I see the democratization of data, the collaboration around these data sets as being immensely powerful in terms of driving capital efficiency from a producer's perspective, but also really serving to manage the perception of risk and the reality of closure for landowners.
And James.
Yeah, and I have to say yes to all three of you. I really like the point that Wes brings up about the democratization. How do we, as an industry, start sharing our information the same way as directions are shared with Google? And what we're seeing is technology moving to the point where we are getting to the point where we can do that. I think one of the big innovations that we're going to see is apparently Elon Musk is going to have his satellite GPS system up here pretty quick. And one of the limitations here in Western Canada has been there's lots of areas that aren't GPS accessible or cell phone accessible. And so we're pretty soon going to be able to share information between field and office just that much more easily. And two very important stakeholders in doing the job right the first time and sharing that information. Complete.
Great. Love hearing about the leading edge. That was a nice addition. So moving on to question number 2. So question number 1 was a little bit of a micro question. We're moving into meso here on question 2, looking at costs and liability reduction. So there are challenges in advancing closure of large facilities, in part related to the scale associated with costing and liability estimation. So in terms of tools and strategies emerging to support more effective management of these sites, how do we more effectively manage large facilities with the scale that we have to deal with? Let's go to Paul first.
Yeah, I mean, obviously I started a company around this, so I think it's pretty important. The ability to synthesize data is paramount. I mean, you can't, that spreadsheet, as I always say, that spreadsheet is just too big to look at. And so environmental professionals are great at finding patterns, but what we need to do is provide tools so that they can do what they're great at, which is make decisions based on patterns and trends. But when you have so much data, you need tools that will help you find those patterns and trends in large data sets, separate sources from each other, fingerprint sources, and you have to understand the chemistry ridiculously well to even begin to try to do that on some of these complicated sites. And so on simple sites, you know, we can take what I always said of my business partner Court is, as I said, I want to take your brain, I want to make it available to the masses. So if I automate some of what you do, anybody can apply it on a simple site. But there is no secret sauce, there is no silver bullet, there is no magic tool that can help you understand the data. There's tools that can help you synthesize it and simplify it and access it on the fly, which is what we're all talking about. But then that gets it to the expert, so that at the end of the day, the expert is still the one who's saying, that's why that trend is there. That's why you're seeing that pattern. And that pattern is associated with that person. That pattern is associated with that source. So the tools are just really to enable the professionals and the experts to do what they do intuitively on small sites with the large data sets that we see on these bigger sites.
Okay, Sheila, with the I guess the large plumes, the sulfur base pads costing, you know, these multi-million dollars, how are you using the tools that were presented in the presentation to accurately predict costs and also reduce liability?
Yeah, so I think like just honing back to the original question, you had tools and you had strategies. So maybe I feel like I've kind of covered off on some of the tool questions. So I'm going to speak a bit more to strategy and how that's sort of evolving, I think. So we are in a time of regulatory change. I think folks of us know, it was mentioned by Sonia Savage yesterday that the AER is working on you know, a change to the liability management framework. So that's in flux, as well as the remediation regulation and the rollout of that. And so, but you know, that's not unusual for us. I mean, working in this industry, we see regulatory change frequently. So I think it's just as ever, it's important to be proactive in sort of our long-term planning. And we see this in my personal work, but also just observing some of the lead clients at work as well. So being proactive in regulatory and stakeholder communication seems kind of critical to facilitate the development of and acceptance of some innovative approaches. And what I've found with some of these sites, it's not something that you close in 1 year. There was a presentation by Trace today as well, where they went through multiple years of work to close off just a small piece of a gas plant facility each year. And so this is something that can go on for a decade or more. What I found is there's multiple regulatory meetings. We got to document those meetings, because you're going to be looking back 10 years later and saying, I met with you or someone from the regulator 10 years ago, and at least I have a document, right? So I'm very vigilant about that. And the other things I see happening is opportunistic research going on, more than I've seen in the past, I guess, when I've been working in this. And folks are also working with traditionally research-focused agencies such as universities and colleges. I think that's awesome, and it gives more credibility and social license to our work. And then another thing that's been mentioned is collaboration. So working with these research programs, we see some industry groups working together and some think tanks. So some examples that have gone on, there's a sulfolane industry group that's looking to try and solve that problem a little bit, collaborating with each other. And there's other examples in upstream, of course. So we see AUR, PRF under PTAC, the Sterilant Research Program that Simone's involved in at Innotech. I do hear recently NRCan is facilitating some research programs as well. And in fact, we had one of the U of A students out with us recently to introduce them to drilling waste assessment and what drilling waste is like.
Great. James?
Yeah, I'm going to just take a bit of that question, and I think one of I'll also focus on strategy, but I think what we need to do, or what would be great if we could do on some of these facilities, is really start to envision what the end goal looks like. So I'll use the Balzac as a plant as an example. I mean, you're right on the edge of Exurbia. Rocky View County is developing warehouses everywhere. And yet the regulatory process seems to be very focused on returning it to some sort of agricultural use. And you have a client who just wants to say, I've spent a lot of money and I'm done. And you have a regulatory process that's, and you may not ever get to the point on a site that big where it meets agricultural type uses. And so what else could you do? Is a rail spur worth money? Like, could you redevelop the site and use it in a different way? So I think we all as society and with the regulator need to envision new ways of dealing with some of these facilities. I'm complete.
And Wes.
James, I'm just going to segue off of what you'd said. When we look at the challenges of closure, one of the things we know are the massive costs associated with these facilities. You couple the massive projected costs with that facility, whether we've applied an internal estimation process that may drive that cost lower than a default to the numbers closure standard, but whatever it is, it still has a CFO saying, really, I need to spend this and I need to spend it soon, or can I spend it much later? And typically the response is, well, let's spend it later because the cash flow constraints in our business won't allow us to free that up. So regardless of the magnitude of the cost of a large facility, it's always large for whomever holds that particular liability. Trying to draw asset closure or asset retirement obligations in nearer to time zero, like today, versus setting it out 20 years and trying to discount one's way to glory doesn't work well anymore for two reasons. One, the markets have caught on when it comes to one's asset retirement obligations and the timing of those obligations, quite critically. The markets are becoming ever more curious and ever more insightful as to what those AROs are and when the cash flow might arise. So if that's the case, really coming up with a robust solution for closing a facility is quite important. We've often heard decommissioning costs or abandonment costs will be pushed out to the right on schedule because we might go back and recomplete that well. How many times haven't we heard that in terms of a base case for suspension? In this case, though, is when you think about large facilities and the energy transition economy that's currently underway and will only continue to grow, where are we potentially leaving opportunities for facilities off the table? So we start considering concepts such as blue hydrogen or other forms of an industrial repurposing of some of these facilities. If you're too quick off the mark, you might abbreviate that opportunity. Unfortunately, though, I think many of these transition opportunities will not need the facilities as they were built. They may not need the footprint as it currently exists, but we don't currently have a regulatory mechanism that would incentivize an owner to close a portion, 80, 90% of the aerial footprint of disturbance, to leave that remaining 10 or 15% alive and well for repurposing. So call it a partial rec cert, even though it's an abomination of the language. Call it some form of interim or progressive closure for which an owner can take credit for the work that's done and meaningfully repurpose the site for economic opportunity. So often is the case, once we've made that decision to close, all we see is red ink. The opportunity to squeeze the asset and management parlance and really try to gain more value, not just for the owner, but for the communities. Don't forget, there's a tax base attached to this. There's all sorts of things that represent black ink or upside to more than just the owner. And I think sometimes we can lose sight of that. So if it's a question of where are the challenges in closure, where are the opportunities in closure also has to be asked. And with that in mind, and with a robust dialogue, again, data-driven, science-driven, with the regulators to look for an approach that works for all parties, risk-balanced, risk-managed, opportunity leveraged, can really be valuable. I know this sounds like a stump speech for a politician, and I don't mean it to, but I really do see the fact that we can bring science and innovation together to really start squeezing out what we did see as just a red ink play in a large facility.
Okay, so last question we'll run through quickly. So we realize that there are a number of these sites that are getting to the end of their productive lives. The last question is really on sustainability and bringing in and balancing effective closure, risk management, and the ESG, or environmental, social, corporate governance piece. So I'll start with James to comment on that last question.
Okay, so I think I jumped the gun a bit on question 2 to start talking about the end goal and what effective closure looks like. How do you parse up a plant into pieces that somebody else can gain value from? I think that's one of our biggest challenges as an industry right now. So I'm going to stop it there.
Okay, Paul?
Yeah, I must be missing something. I guess I'm a bit of an outlier, but I don't like, I think there are mechanisms for leaving the last 10 to 15%. I recalculate the site-specific liability assessment, and I discharge 90% of my client's liability, and I leave them with 10%. Same thing with the Balzac plant. I would leave that as industrial. There's no need to return it to agricultural. I mean, we can leave that as industrial, and as long as the continuing land use, the continuing zoning for that site is industrial, then there's no issue with that. It's the person who changes the land use who's responsible to bring it up to the current land use. So sure, if a farmer buys it, then that's another story. But if you can expand cross iron mills or whatever the heck it is down there to include the footprint of that plant, you're going to be allowed to leave it as commercial or industrial. So I think these mechanisms exist. I think we just need to apply them correctly within the existing framework as much as possible, because we are not going to change the framework anytime soon. It's not changing. Things are only, there's no way we're getting increased certainty or a reduced requirements anytime soon. So we just need to learn to use the existing system to serve our clients and the environment. But again, I could be completely missing something there.
Do you have any thoughts, Sheila? In terms of
Yeah, so
sustainability?
it is interesting. I guess the only thing I'd say to add to what Paul's saying, I kind of agree a little bit with what he's saying, although I think you do it in small steps. So, and that's kind of what those initiatives I was talking about, like Simone, you're working on that Steriland program. Okay, that's more, I think, more related to electrical utilities at this point. But regardless, I mean, that initiative is to find ways to deal with this issue, develop, perhaps do research to support improvement of the guidelines or understanding of that issue. And then that would support regulatory change eventually if there's a need to change the tier 1 value or such. And so I think it takes just kind of a long-term vision and for some issues. So for example, as we talked about, there does seem to be some challenges with applying that sulfur guideline, which the S2 presentation flagged. We see with there's a guideline allows certain treatments of sulfur, but at the end of the day, you wouldn't get closure by closure definitions because you would not meet your groundwater concentration in sulfate. Now that may work at the Balzac because you have background sulfates, but some gas plants that I work at do not. They don't have sulfates at the level that you would get from gypsum dissolution. And so I feel that needs to be relooked at, to have some grandfathering for sites where historical practices were considered acceptable. Seems it could be approached in a similar fashion to the D50 equivalent guidelines, et cetera, that we've used for drilling waste. And if we think about drilling waste, the province has come up with a pragmatic way of dealing with that material. And I think this sulfur-based pads need to be relooked at in the same fashion, been around for decades, as we've mentioned. And I think there was talk about, full cost accounting of remediation. So starting to think more about sustainable remediation and the cost of greenhouse gas emissions and all those things that come into play when you're using literally hundreds and hundreds of trucks and hauling material to landfills and so on. It would seem that the Canadian market is open to that, right? They say that our investors, both in Canada and European investors and so on, are interested in ESG principles.
Thank you. And Wes.
So the concept, thank you, Sheila, for bringing up sustainable remediation. It's so critical to, I think, the future state of effective asset retirement obligation, both here in Alberta and elsewhere around the world, really finding that balance of trade-offs between opportunities and risks. And so often when we hear the word sustainable from an industry perspective, we hear cost, we hear red ink. But the reality is sustainable means it's there for a while and it's got to be perpetuating itself, which means by virtue of that we're putting energy into the system. We're building black ink out of it. So risk and opportunity need to be effectively balanced when it comes to sustainable remediation. And to that end, when we think about remediation, whether it be a large facility or a well site, so often is the case, unless there's offsite contamination, our viewpoint is constrained to what the fence surrounds. That's it. What lives inside the fence is where our liability starts and stops. Potentially, and indeed, to Paul's point, maybe liability is shared amongst many actors. Start thinking about the costs of remediating a site beyond just the greenhouse gas component, which a lot of people focus on. But look at all of the ancillary other components of moving equipment, whether it be VOCs as you open an excavation and haul contaminated material, whether it's PM 2.5 and PM 10, whether it's road damage and destruction that you bond against, whether it's traffic congestion in a small town that waits for 40 trucks to pass through it. All of these things impose potential costs that need to be reflected as remediation is being considered. You know, put that up against the opportunities. There's economic advantage to be had for sure. You move yellow iron, you're generating a wage economy. But as you find these balances with sustainable remediation, you start doing another thing. You start announcing to not just your shareholders and to the regulators, but to the world that's investing in your company, that you're thinking about your actions and the actions of others in your business from a risk managed way, from an opportunity leveraged way. And indeed, ESG, Mark Carney had a great quote a few weeks ago that said, ESG is about managing risk. Sustainable finance is about really managing where opportunity lives. And if you take a look at the emerging field of sustainable finance, even here in Canada, the green bonding principles clearly lay out that sustainable remediation, particularly that for soil, is something that you can create a green bond for. So imagine you carry an ARO on your balance sheet already, turn it into a debt instrument that's green bonded at a relatively low yield rate, and start affecting your closure using the green bond. Now I'm stepping way out of my comfort zone when I say stuff like this, but I'm just trying to tickle your imaginations around what can be done. So sustainable finance and ESG don't necessarily have to mean bad things to the energy sector. They can mean that there's areas of opportunity to capitalize our investment in decommissioning as we start down the path to energy transition. But most importantly, demonstrate to stakeholders, all of whom, from shareholders to landowners to regulators, that there is balance that can be readily achieved with sound science that protects them, but can be well financed.
Great. Okay. Well, I think we're over time. So just a quick wrap up. We heard about regulatory, ensuring regulatory buy-in using various communication mechanisms and tools, maintaining social license, enhancing collaboration, and thinking about an end goal, especially on these large facilities, and what that looks like, and mechanisms to make that clear to all stakeholders. And I think another theme that sort of came out in the discussions was looking outside the boundaries of one facility. So whether that's a collaboration opportunity or a reuse opportunity, or understanding what background conditions are beyond the boundaries of your site, and also what you may be releasing to the air as you conduct your work. So thank you everybody for participating, especially to the panelists, and we will wrap it up.
Thank you.
Thank you.
Thanks very much.